Hi, today I'm going to talk about sampling and optimization on Riemannian manifolds. So what we want to understand is convex programs on Riemannian manifolds. Okay, so let's quickly go over what a convex program in the Euclidean space is. So you have a convex set and you have a convex function f, and you want to minimize this convex function over this convex set, convex function f over this convex set k. Okay, so what are manifolds? What you should keep in mind is a smooth surface in 3 dimensions, like a torus, a double torus, a sphere, or something like that. Manifolds are essentially high-dimensional generalizations of these. So examples you should keep in mind again are spheres, hyperbolic space, torus, Lie groups, the Grassmannian manifolds. And recently, manifolds have drawn a lot of attention in machine learning. Okay, so what we again want to understand is a convex program over a manifold. So what is this object? Let's try to understand what convexity on a manifold means. First, let's look at convexity over Rn. A convex set is a set such that if you take any 2 points in the set, the straight line joining these 2 points is in the set. Okay, so what is an analog of a straight line on a manifold? And these are these things called geodesics, and you get them by noting that the straight line between any 2 points in the real space is the shortest path between those 2 points. Okay, so a geodesic convex set is a set such that the minimizing geodesic between any 2 points is contained within the set. And similarly, a geodesic convex function is a function if you restrict to unit speed geodesics, you get back regular convex functions. Okay, so this is a picture to keep in mind. There's a convex set M, there's a set K, and this wiggly thing is a geodesic between those 2 points, and it's completely contained within the set. Okay, cool. So now we define convex programs over manifolds. So you take a geodesically convex subset K and a geodesically convex function f, and you want to minimize this over the set. Okay, so our aim is to design efficient algorithms to solve these problems. Okay, again, a quick note on the access model. To abstract away details of realization of the manifold, we'll take the exponential map as an oracle, and for the convex set, we look at the membership oracle. Okay, cool. Convex programs over manifolds is a well-studied problem. There are books on this, and first and second order methods have been studied extensively. More recently, there have been lots of interest in this area in machine learning and TCS. If you attended Avi's talk, he mentioned this extensively. But again, to our knowledge, we don't know how to solve this over a general class of manifolds with the constraint of a convex set. Okay, so let's try to generalize Euclidean algorithms to manifolds. So it's not immediately clear how to generalize things like ellipsoid and interior point methods to manifolds, but there is this other neat connection, which is sampling and convex optimization. There are these very nice algorithms that tell you that if you can sample on a convex set, you can optimize on this convex set with a catch, but that's fine for now. Okay, so the algorithm that we'll be interested in is simulated annealing, which you have a temperature schedule and you sample continuously as you vary the temperature, and eventually you'll get to a minimum. Okay, so the question again we are interested in today is, does simulated annealing generalize to manifolds? That leads us to the following questions. Can you sample efficiently over convex sets in manifolds? And given that, does the connection between optimization and sampling continue to hold over manifolds? Okay, and we try to answer these questions over positively curved manifolds. Okay, so again, a quick slide on curvature. These are the 3 settings you have. The first one is negative curvature. The second one is 0 curvature, and positive curvature is like a sphere. Okay, so for the first question, again, to sample over convex set in the Euclidean case, what the standard technique is something called geometric walks, and quick note is that the natural ball walk on manifolds doesn't work, but there is this neat walk called the geodesic walk, again introduced by Lee, Vempela, and Mangubi and Smith, where you basically take the step along the exponential map in each turn, and since you have a convex set constraint, you reject the step if you're outside the convex set. Okay, so again in pictures, the outside blue set is a big manifold, the inside blue set is the convex subset you're interested in. You take a step from x1, you go to x2. If a step says go outside the convex set, you don't go, and if it stays within the set, you continue going there. Okay, so quick slide on this thing. We show that with technical restrictions, we show that the geodesic walk on a convex set actually warm start mixers in polynomial time. Okay, so the second question was, does the connection between optimization and sampling continue to hold over manifolds? And again, the algorithm of our interest is simulated annealing. And we show that again with all the conditions of the previous theorem intact. And if you have a Lipschitz continuous geodesically convex function, we show that if starting from a uniform sample from K, you can actually show that the simulated annealing algorithm runs for polynomial time and outputs an epsilon minimizer. I have a quick slide on the techniques that we use. The main technique is this amazing thing called the Clartag localization theorem on manifolds, which basically is a manifold analog of the Kannon-Lowas-Simonovitz type localization theorems. Okay, that's all I had for now. Okay, so one thing that so manifolds that people care about, again, recently are these PSD manifolds, which does not fall into our setting, but you can show that these operator scaling problems actually you can think of them as geodesically convex optimization problems over this manifold. So, and it has had sort of very nice impact on complexity. That is one example.
And what is the condition that the PSD manifold violates?
So